Okay, MT149. Well, this is going to be basically lecture 2. We're going to start with chapter 2. This is the fluid power systems. So I'm going to I broke this up a little bit more, try to make it a little bit more interesting, hopefully. I'm going to try breaking this up and say some videos of actual things happening. Well, YouTube, I would say. Not necessarily anything I'm going to necessarily make outside. But this will allow you to basically correlate the things we're doing in class with some stuff outside. I usually do try to incorporate some videos into my classes, but trying to do the best I can with what I got right now. Alright, so objectives of this is really to give you the overall view of what's involved in a fluid power system. So the objectives here: explain the function of the fluid power systems, identify the basic structures of the fluid power systems, list the basic components, the component groups involved in the structures of fluid power systems, so the basic work performers and control devices. So functions of the components involved in the basic fluid power systems, describe similarities between hydraulics and pneumatics. So there's a lot of similarities between hydraulics and pneumatics. Explain the operations of basic hydraulic and pneumatic systems. So go over basic operation procedures, so on. Alright, so that's the overall objectives there. Really what a fluid power system is, they're made up of components designed to perform specific tasks. So they have a specific task in mind, you have a specific job in mind to do work, right? So these components act together to perform desired work. So your 5 performing functions in a fluid power system, hydraulics, pneumatics, either one, you're going to have these 5 systems, and really I'm going to start at the top. It doesn't necessarily matter the way they built this, but fluid control, so we have to control the actual circuit itself. What we're going to want to do, we want to control the amount of work done, right? Work performance, fluid conditioning, energy conversion, yes, energy conversion. So going from hydraulic to mechanical or mechanical to hydraulic. Fluid distribution, how is that fluid getting distributed through the system? So those are the 5 main performers. So those are the 5 required system functions to have a fluid power system. The fluid power systems are structured using component groups that perform specific system functions. So there's actually 5 different groups, right? Makes sense. I guess there's 5 different performing functions. There's 5 groups. So there's power unit group, there's the actuator group, there's conductor group, control valves group, and the fluid maintenance group. And we're going to go through each one of those groups, so I'm going to continue on. And as you're looking through this, just mention it quickly. These red indicators here, if you had I'm going to post this up on Blackboard, and you can actually click on those and it'll take you right to definitions and things. So if you wanted to know, say, what a prime mover was, you could click on it and it'd go tell you. Okay, well, power unit group. So the first group we discussed, this deals primarily with energy conversion. So again, the big thing for hydraulics is energy conversion. Consists of prime mover, pump or compressor, reservoir or receiver, depending on if you're pneumatic or hydraulic, right? So this is what actually moves your fluid. The actuator group performs the work of the system. So this consists of both the cylinders and the motors. So again, it's another conversion. You're going from hydraulics to mechanical for actuators. So these perform the actual work. It's what does the cutting, and it's what does the work, right? In this case, we're linear action cylinder, but this also is for motors. So as long as it's actuators, you think actuators, moving devices, That's also the most dangerous group for hydraulics, right? We went over that for last week's safety PowerPoint. Our conductors groups. So conductors, I always like to compare hydraulics and pneumatics to electricity, since it's all the energy flow, right? It's all has to do with energy flow. In this case, conducting energy is done through pipes, tubes, and hoses with hydraulic power or pneumatic power, right? So conductors distribute the fluid throughout the system. So anytime you have a hose, a pipe, those are going to be your conductors. Control valves group. So it controls fluid pressure, flow direction, and the flow rate. So control valves, it does the controlling, right? So it's the control it does is either directional, pressure control, or flow control. So there's only 3 different types of control, and those are the 3 different types of control valves out there. Fluid maintenance group. So think filters, filtration. You're trying to remove dirt, moisture, excess heat. So these are typically seen as filters, but you could have anything from like a heat transfer device, or just pressure. Well, sorry, not pressure. This removing dirt, so particulate with a filter. Moisture can be removed with particulates or sometimes with pressure drop. We'll look at that later on in the semester and talk about that when we get to physical properties. Alright, so power unit. So getting into our actual power unit devices. So that was a power unit group, right? What is a power unit itself? So just to go back, there was our power unit group. So I didn't necessarily mention it. It consists of, so your power unit, multiple different types of power units out there. But really, prime mover, what is a prime mover? Well, prime mover is either an electrical, for our case in our labs, it's going to be an electrical motor. But it could also be a gas powered motor, so diesel, or your typical gas that you get for your most vehicles out there. Well, it depends, I guess, what country you're in, but typically it's going to be electrical. If it's plugged in the wall, if it's outside on, say, one of those excavator pieces of equipment, one big piece of equipment, it's probably going to be gas powered. Reservoir receiver, this is what holds the fluid, right? So that's what's making, or basically transferring the power. So that'd be your reservoir receiver, just as a place to hold the excess fluid. Alright, so those are your power unit devices. There's a lot of different types. Power unit itself, so as I mentioned before, power unit is your electrical motor or internal combustion engine. So are often the 2 types of prime movers out there. Your pump or compressor produces the fluid flow. The fluid flow is created by your internal pressure differences. We'll actually talk more specifically about a pump later on. Either, I think it's next lecture or the one after, soon. It's one of the first chapters we do. Fluid flow transmits energy through the system. So your power unit essentially takes that energy, electrical energy or gas-powered energy, turns that into hydraulic energy, and then that gets transmitted to your actuators, which then does the work. Your power unit system, reservoir, receiver stores system fluid. So your power unit itself has basically a big storage device, typically a pretty decent storage device depending on how big your system is, and that stores that extra fluid. So your pump has to bring fluid from somewhere to create that fluid flow, right? Receiver also contributes to system temperature control and fluid cleaning. So receiver reservoirs have heat transfer devices on them to cool themselves down. You typically want not much of a temperature change, especially for pneumatics. Again, something we'll talk about later on. But temperature tends to have a lot to do with, again, energy loss. So you don't necessarily want a lot of energy or temperature creation, but we'll get more into that later. We'll not get too far into the physics for this class, but we'll talk some about that when we get in, especially pneumatics. Actuators. So actuators are typically what does the work, right? So in this case, we have cylinders that are used for hydraulics and pneumatic systems, and you see these cylinders, linear motion devices here. Really, you're used on a lot of different devices. So this case, it's for turning, but there's a lot of different devices that actually use this. Actuators here, another one, rotary actuator, motors, right? So if you have rotational energy, you're going to have a motor. And this is actually the motor down here, which then eventually gets, I think it has some sort of gearbox in there that translates to a pulley. Your actuators. So in your actuators, motion is created when pressurized fluid moves in an internal part of the actuator from a high pressure area to a low pressure area. So in general, that's how all the fluid moves, right? You go from high pressure created by your pump to a low pressure. Essentially for hydraulics, it eventually goes back to your reservoir, which is at atmospheric pressure, which is 0 psi. So it's going from high pressure of the pump back to the reservoir. So you end up getting this high pressure to low pressure, and that's just how the system works. So that's how your actuator works as well. And I believe this video, I'm going to check on, well, let's try it here quick. I don't know how well this will play, or record, rather. But what we can see in this is just a simple rotary actuator. It has a stop here. And you can see where high pressure is created. This one has low pressure connected to the reservoir. And when it starts moving, which, give me a second now. Here we go. So a high pressure comes in, and this low pressure area goes out, and switch it around the other way with our directional control valve. We can get it to go the opposite direction. So that's just one example, and there's a lot of different ones. I'll post this video, or I'll post the presentation really, but you'll have the video for that if you want to see more of those. I found a video that showed a lot of different actuators. There's some neat ones in there. So here's another actuator. So your cylinder actuator, what is it created of? And this is something, again, we'll go into a bit more when we get to actuators, the chapter on actuators. But basically you have 2 ports. And it's kind of how we saw that other, except for this one's just linear actuation rather than rotary. So we put pressure on this side. Pressure fills this chamber in here, pushes against that. And this is free floating, so it can actually slide, right? So all this fluid that's in here gets pushed out and goes back to the reservoir, and this extends, and vice versa to retract it. So we'd have high pressure in here to retract, and anything that was left in this side goes back to the reservoir. Alright, conductors, pipes, tubes, hoses. Again, they transmit system fluid to system components. So I'm not, again, going to really spend a lot of time on some of these repeat slides. I think I hit back there on accident. Control valves. So directional control valves. This is the other group there. So vary the direction of movement from a cylinder or a motor. So I mentioned that before. If we wanted to get to say, reverse the direction, we would reverse the directional control valve. And here's again a quick video. It seemed to work all right. So this one's kind of neat. This is a video that shows, so T is tank, so it means it's going back to the reservoir. P is pump, I think, pump or pressure. And then we have side A and B here. So, side A or B could be like our, where is this? So A and B here, import A and B, for example. So we go back to, where did I put that? Yes. And when we watch this, so we'll actually see, put that down. We'll actually see this, how to read those schematics later on. But you can see the way this is flowing here, it's going back to tank. So it's coming from our pump, going back to our tank, right? He puts it into the neutral position, so it shuts everything off. So notice how this can go really two different directions. So when you switch to the other direction, which I think is here in a second, just go to it. So now we switched our P and T here. So our pump now is pushing through A and returning back through B and going back to tank. So depending on which way we twist this, we'll end up getting a different direction of flow, hence directional control valve, right? So that's your, I guess, crash course into control valves. Directional control valves. So there's directional control valves, pressure control valves control pressure in a fluid power system. So this restricts fluid flow into a part of the system or allows fluid to return to a low pressure area after a desired pressure is reached. So main thing here is really control pressure in a fluid power system. This is what we were setting when we, especially the first lab, we've only really used those once. You'll be using those again next week. But when we control the pressure on those pressure control valves, we actually set, I like to say, limit the system pressure, because what you're doing is the pump's trying to push out as much pressure as possible, really. And what's happening is I don't have a good image right now, but basically what's happening is you're allowing some of that fluid to divert back to your reservoir to lower the pressure, and whatever is left goes into the system, right? Or whatever's left really gets dumped, but you're setting, say, 60 psi, for instance. So 60 psi is going in the system, but really there's enough fluid there to make, say, 100 psi. So 40% of that is getting diverted then back to the reservoir. So this is essentially how a pressure control valve works. We'll actually look at the physical component in lab. We'll use one. We won't necessarily take one apart, but we'll look at the internal components and how they internally function later on in the semester. Control valves. So another control valve is flow control valve. So flow control valve, think, we're controlling the flow. Think how, when we think flow, we should think how fast, right? So how fast is it flowing? How fast is the river flowing, right? So that's typically, flow is thought up of more speed. So really, control valves, looking at fluid control valves, what you're doing is you're increasing or decreasing the speed of, say, an actuator by increasing or decreasing the speed, right? So it fills that chamber of the actuator a lot quicker, so you increase the speed. So flow control valves, really what you're doing is you're limiting or increasing or decreasing the amount of fluid flowing through the system. And that's typically done with one of these called a needle valve. And what you're doing is, you can kind of see the way they try to do with molecules, I guess. Molecules flowing in, water molecules flowing in, or hydraulic molecules, oil molecules, getting kind of compressed here. So you're going to typically have a higher pressure. You usually get some pressure loss, energy loss for pressure drops without any energy being done. But you're able to, again, restrict flow. It's like, my usual example is putting your thumb over the garden hose, right? So that's kind of your needle valve there. How closed you have it increases the speed, yet it decreases maybe, not really, decreases the amount of flow area, I guess, is the thing I'm trying to think of. So if you think of this, your flow area, cross-sectional flow area is decreased, speed is increased, typically, especially out of the orifice. But that's, you're thinking of, again, that would be your thumb over a garden hose. Right on the outlet, yeah, it's sped up, but you're thinking that would be more of a nozzle case, I guess. In this case, it's more of decreasing the speed the more you have your thumb over it, because you're actually decreasing the flow rate, right? Sorry, so maybe the thumb over the garden hose isn't the best thing to think of there. Fluid maintenance devices. So maintaining a fluid, right? So you want to maintain your normalcy of a fluid. So either particulate, how much particulate's in there, separators to keep fluid out of, say, your pneumatic systems. So water out of your pneumatic systems. Lubricators can spurt lubrication into, say, a machine or a device you're using. So say your cylinder doesn't start catching or seizing up after 100,000 repetitions, or if it's moving really fast, right? You need to keep things oiled. Used to remove contaminants, condition the fluid is really the main objective of a maintenance device. So you're trying to remove contaminants or condition the fluid, either temperature, particulate, keeping it the same viscosity or humidity in that case for pneumatics. But this assures effective system performance and acceptable service of life. So again, if you don't oil something, obviously it's going to burn out quicker than if you did, right? So that's your maintenance devices. Hydraulics versus pneumatic systems. So these are very similar, and actually a lot of even the graphic symbols are very similar. In this case, comparisons can be made between hydraulics and pneumatic systems. And I'll let you know when, there's a lot of those that can be made, but there's, in some cases, you're going to have a variation. So system technology and designs will vary typically between hydraulics and pneumatic systems. One will be heavier. Hydraulics is heavier than pneumatics. You typically have, your main difference there is compressibility. So hydraulic system operation, how does that differ? I think they differ for, okay. So they're talking about operation here. So hydraulic system operation, we have movement of oil originates at the pump. So we have oil from our reservoir coming from our reservoir to our pump. So as the pump draws in, we'll talk about the how the pump works, but a pump draws essentially the fluid in to the pump, and then it pressurizes it, pumps it out, right? So the pump actually creates the fluid flow, and there's a filter at the pump inlet, so any particulate gets caught. We can't get dirt up into the pump. High pressure at the pump is basically forced out, right? So after we get that drawn in through the reservoir filter, pump inlet filter, we pump it out, and system eventually gets over to the actuator. Actuator performs the work. The pressure control valves limit pressure of the system. Flow control valves control the speed of the actuator's movement. And then eventually oil is returned to the reservoir. So in hydraulics, you always think of the oil recirculating. So the oil just keeps going through the system. Pneumatics, this is different. Pneumatics, movement of the air begins at the compressor. So compressor draws air in from atmosphere, right? As air moves into the system from the atmosphere, it is filtered, compressed, stored in the receiver under pressure. So the receiver is those big tanks you see. We'll talk a little bit more about the reasoning for having those, but that's where all your energy is stored. So that air is pressurized, brought up to a pressure that you've turned up your compressor, what you want your compressor set at for pressure. And then pressurized air is then distributed to the system workstation. So where are you doing the work, right? To your machine or device that you're using. And then at the workstation, the pressure is regulated. So you will find in our labs, we'll have pressure regulators. I don't know, you probably don't have, you have pressure regulators even in your home compressors, but you might not have a workstation pressure regulator set. So you'll see how those work. About a little over halfway through the semester, we'll have those up and use those in lab. But a filter and lubricator is also included into the workstation, typically included into the workstation, I should say, because we don't really have a lubricator in our workstation FRL unit. And getting ahead of myself there, but anyways, typically that all gets done right before you get into the system. So you pressurize. If you're going to lubricate your system, you're going to do it there. Filter again if you have a certain filter parameter set for your machine, and then air is then moved through the control valves onto the actuator or machine you're using it on, and then the system work is performed by the actuator. The thing with pneumatic systems is air is always discharged back to the system, or back to the atmosphere. It does not stay in the system. So after it passes through the system, it's gone. It's not coming back in other than if it gets pulled back in through the compressor. But at that point, it goes through the whole stage again. So I did miss one. During system operation, you have fluid control valves that control your speed of your actuator movement. So you see a lot of similarities there between your pneumatic and hydraulic systems. But again, there's a little bit of a difference with where it's really drawing the fluid from. In this case, pneumatics drawing fluid from air, where hydraulics is drawing its fluid from a reservoir. But that was really what I wanted to go through for this lecture. It's getting close to 26 minutes. I know it's not a full 2 hours. What we're gonna do is I'm gonna have an assignment for you, and we're gonna start drawing out graphic schematics. We're gonna start very basic. I'm gonna ask you to do a couple different control valves, and you draw them up. You take a picture of them with your cell phone or camera, and you'll post the picture up online. If you have any questions, we can obviously talk through email, but next week, really hopefully you'll have it done by next week. But if you really have some difficulties or some questions, concerns, we can discuss it in lab next week on campus. But please do let me know if you do have a concern before that. Don't wait for next week. Might as well get in touch with me now. All right, but that's it for chapter 2 lecture. I guess that's what I'm going to be doing for lecture 2 anyways. I kind of chunked it out a little bit, but I'll be posting this PowerPoint up online for you guys to see the videos if you want to watch those full videos. All right, well, hope everybody's staying healthy, and I'll see you next week. All right, bye.